Alright, so now we're going to look at a method to calculate the varying temperature profile of our bar, right? So our axis. So if we imagine we have a bar here with a certain amount of heat, that heat will diffuse within the bar. If we heat one end, it eventually will heat evenly throughout the bar over time, right? And so that's a big thing to remember, is that this is all over time. And so the way that we're going to look at this, especially when coding, is we're going to split the bar up and look at the temperature at different sections. So basically different points, but they're going to be sections of the bar. So for this quick example, let's say we're going to split our bar into 10 sections, right? Okay, 9 sections. I ran out of room. So 0 to 8, 9 sections. We are going to start numbering from 0. And now the way we're going to refer to this in our equations is going to be through our temperature, just general T for temperature, right? And then it's going to be little t for time. So the temperature at a given time and at a given position, x, right? So position and time. And then if we, just to show you what I mean, right? If we take the 5th section here, or section 5, right? It's going to be T at position 5, and the time, we're just going to say it's 0, right? We're going to, if we're imagining we're imagining that this bar has been heated thoroughly or hasn't been heated yet, right? So, you know, the time, depending on how long we run our equation for, right? Over time, that will obviously change, and the temperature will as well. And so we have to kind of look at finding that that temperature at a given time and at a given space, right? So we're basically going to be solving for a value of T here. So we have to go back to the thermal diffusivity equation in the first video. And so change in temperature over change in time is equal to thermal diffusivity. And then from there, we're actually going to split this equation up so that it's easier for us to work with. And we're going to, so it was basically the change in x squared. So is the second derivative with respect to time over the derivative of x squared. So we're going to split that up, and then we have a dt, and then a dx. Right, so x squared, and then with respect to the second derivative of time. And so now we can kind of input this value of t into our t values, and then sort of understand what values of t are going to help us solve this this problem. So if we look at this right here, we get the change of time, or change in temperature over change in time. So it's just going to be t of x, right, and time. So if we do time plus 1, right? So say it's 1 second or 1 unit of time after the previous one, right? So this is basically change in temperature. So T plus 1 over T over the change in time. So that is what we're solving for, and then on this side, right, we have our alpha, and then up here we have, let's see, a change in x, right? And we're still going to use the same values over here because these also account for a change in position. So if we do x plus 1 minus the position slightly before that, right, x over change in position, and then that is multiplied by we have our change in time over change in position, and so that is going to be t minus 1 x minus x, and that is over also the change in position, and then all of that is going to be under all that's going to be divided by the change in position. Okay, and so now we're going to shove everything to one side, and we're going to be solving for this temperature value in the near future, right? In one time unit past our previous, right? And of course, we're going to continue this these calculations with a loop in our code. So we basically get our t plus 1 at a specified position on this side, and now we get our tx, right? This is our this will be our previous value, and then plus, and this is how we calculate that difference here, right? So plus we get tx plus 1 minus alpha, our thermal diffusivity, tx and I made a mistake up here. This is actually, we're still looking at our change in position, not our change in temperature or time anymore. So this is one position before that, because we need that value to then calculate the change that is to be in the next one, to be in our next value. And then plus tx minus 1. And that is all over delta x squared, just because we're combining these, and then multiplied by the change in time. And so now if we simplify this again, we can simplify this basically by getting rid of these values here, because our change in time and change in position are going to remain constant. Our change in time and change in position are going to remain constant, as well as our thermal diffusivity out here. So if we define a value of R and equal that to our alpha, I guess we'll do change in position squared, and then over the change in time. This sorry, I got that backwards. It's going to be the change in time over the change in position squared. And basically that will replace a lot of these variables in our function with one variable that we can calculate and then use multiple times. So one quick rewrite, x t plus 1 equals txt plus r, right? And if you ever wanted to go back, you can always multiply this r value by what I'm about to write in parentheses here. And it's essentially just what's up here, right? So tx plus 1 minus alpha. We still have a thermal diffusivity value on this one. txt plus tx minus 1 t. And then this is what we'll use to solve for the thermal diffusivity, or the heat over time as it diffuses throughout our bar.